Okay, our final section in Chapter 3 deals with the graphs of rational functions. A rational function is basically where both the numerator and the denominator have polynomial functions in them, or at least the denominator does, so that we have fractions. However, there is a very important restriction. The denominator part cannot equal 0, so that will create spots, if you will, on the graph that the domain is not allowed to be. So, for example, in x plus 1 over x minus 1, we cannot let x equal 1 because 1 minus 1 is 0, and we're not allowed to divide by 0. Now, the x can be anything else in this case except for 1, but that means that at the value x equals 1, we are going to have a discontinuity. Our graph will be broken at that particular spot. Rational expressions can be reduced just the way ordinary numerical fractions can be by canceling any common factors, such as 4/6 being reduced down to 2/3. Likewise, if I had x squared minus 1 over x plus 1, x squared minus 1, difference of two squares, could be factored into x minus 1, x plus 1. The x plus 1s could then be canceled. However, I'm still not allowed to have any value of x that would make the denominator 0. So that is a limitation. All right, we're going to look at a couple of examples. I want to zoom in so it's easier to look at. These are in your text. The first is an example of 1 over x. Note x cannot be 0 on the graph. So our domain is all values of x except x can't be 0. And the range ends up being pretty much all values of x as all values of y. However, it's not going to equal 0 either. Because, of course, it's 1 over x. So there's no way to turn that into a 0, no matter what x is, since we can't use the 0. Please note that it's discontinuous at x equals 0. There are two lines that we call asymptotes. They bound, if you will, what the graph looks like, or they cut it into pieces. That's another way of thinking about it. One of these asymptotes is the y-axis. That's the vertical one going up and down. The graph does not cross the y-axis. It comes up very close to it, but it does not actually ever equal the y-axis. There's no x that's going to give me y is 0. Likewise, the x-axis is a horizontal asymptote. There's no way, I can get close if, like I made x equal infinity, then that's pretty much going to be like really close to 0. But of course, since you never can really get to infinity, you never really get to the 0 either. You just get smaller and smaller and smaller. This is considered an odd function because notice that if you have negative x values versus positive x values, how the graph gets flipped. And so what you see over here versus what you see down there are just flipped in terms of sign values. Here is a graph of 1 over x squared. So it has the same two asymptotes because, again, there's no way to make x equals 0 because then it'd be dividing by 0, which means then there's no way for the function to have an output of 0. And so you have the same two asymptotes, the same two bounding lines. The difference is this is an even function because whether I plug in positive values of x or negative values of x, the square turns everything positive, and so you get the two curves, if you will, going upward the closer they get to the y-axis, and then they level out as you go to either positive infinity or negative infinity. And so you have the symmetry is about the y-axis, whereas in the other one, the symmetry was about the origin. So some examples of some graphs and pieces of them where they become discontinuous at x is 0. Now, just to go on, the two graphs above are some of the simplest rational functions. Again, they're each broken by vertical asymptotes at x equals 0 and horizontal asymptotes at y equals 0. The graph of 1 over x squared is broken by the same things. Vertical asymptotes can be found by setting the denominator to 0. If the numerator has a lesser degree than the denominator, so note in both these cases, the numerators had a degree of 0, there's no x term, and the denominator was greater than that. If the numerator has a lesser degree than the denominator, then there is a horizontal asymptote at y equals 0. If the numerator and denominator have the same degree, the horizontal asymptote will be at y equals an over bn, which is basically these are the coefficients in front of the greatest degree for the numerator and denominator. And we'll look at an example of that in just a moment so we see how that goes. If the numerator has a degree 1 more than the denominator, then there will be an oblique or a slanted asymptote. To find it, divide the numerator by the denominator and then disregard the remainder. Set the rest of the quotient equal to y to obtain the asymptote. And so basically, we're going to have a line like y equals mx plus b. Or it could be even y equals b, depending on the type that we found through the division. And this, again, mx plus b, that's just slope intercept of a line that is a diagonal. If you have both f, y, and x, you have a diagonal. All right. Let us look at some examples. And first, we just want to find if there are any vertical, horizontal, or oblique asymptotes. Okay, so for vertical asymptotes, and we're going to just use VA short for vertical asymptotes, we want to set the denominator to 0. So x minus 4 equals 0 gives us x equals 4. That's a vertical asymptote. So that means the line, it'll be a vertical line, the line going up and down at x equals 4, the graph will not cross that particular point. In terms of domain, x cannot equal 4 because that would give us a 0 in the denominator. Now, for the horizontal asymptotes, which I'm just going to call HA, where you have equal degrees for the numerator and the denominator. Here's the way to find them. Okay, so we're going to go f of x equals 2x plus 6 over x subtract 4. Now, since x is the biggest degree we have, we're going to divide everybody by x. So it's going to be 2x over x plus 6 over x. And then in the denominator, x over x subtract 4 over x, which the x's here cancel, and basically I'm going to have 2 plus 6 over x. And then x over x is just 1 minus 4 over x. Now, basically, as x, the absolute value of x, goes towards infinity, these terms that have divided by x will basically go towards 0, and my function will end up going towards 2 over 1, because these parts will get smaller and smaller, totally insignificant. So the horizontal asymptote will be at y equals 2, 2 over 1, y equals 2. So again, this is when the degree in the numerator and the denominator are the same. And if I'd had x squareds, then I would have divided everybody by x squareds. Anything that ends up with an x in the denominator, as x gets really, really big, that term gets really, really small to the point of being insignificant. And it's just the terms that do not have an x value in them is the line, in this case the horizontal asymptote, that this function will approach. All right, in my next example, notice that numerator has a degree 1 higher than denominator. Okay, x squared on top, only x on the bottom. So the first thing we're going to do is long division. We don't have a x term in the top part, so we got to put one in. So I need an x. X times x will give me x squared. Subtract x. I want to subtract all of that. X squared to be gone. I'll end up with an x plus a 4. So now I'm going to do plus 1. So 1 times x will give me x. 1 times minus 1 will give me minus 1. Now we subtract this, and I get the 5. So that means f of x equals x minus 1, x plus 1, plus 5 over x minus 1. Here's our little remainder part. Now, as x gets really big, goes towards infinity, the 5 over x minus 1 will go towards 0. It'll get smaller and smaller and smaller to the point in which it's totally insignificant. So that part will be gone. The other part, the x plus 1, will be our oblique asymptote. Okay, slanted line at y equals x plus 1, so m, the slope is 1, and in this case, the y-intercept is 1. Now, in terms of the vertical asymptote, that's still the denominator, so the vertical asymptote will be at x equals 1. So this is our O, A, and this is our B, A, vertical asymptote. So, just a little bit of following the rules to find, is there a vertical asymptote? Is there a horizontal asymptote? Is there an oblique asymptote? Notice that part B there did not have a horizontal asymptote. All right. Couple more examples, and then we're also going to graph them. So let's see. First off, vertical asymptote, x plus 3 equals 0. So x equals negative 3 will give me a vertical asymptote. Now, since the degrees are the same, we're going to work on the horizontal one. So we have x minus 5 over x plus 3. Now we're going to divide everybody by x because that's the biggest degree. So we're going to have x over x minus 5 over x. And in the denominator, x over x plus 3 over x, which will lead to 1 subtract 5 over x over 1 plus 3 over x, as absolute value of x goes towards infinity. Then that means those parts divided by the x will become less and less significant, and basically f of x is just going to go towards 1 over 1, which will lead to the y equals 1 as a horizontal asymptote. So we have a vertical asymptote and a horizontal asymptote. Also, if we find the x equals 0, the y-intercept, we get 0 subtract 5 over 0 plus 3, or negative 5/3, which is the y-intercept. All right, so we want to graph this, so let's make a little t-chart of some values. And I like using x and y whenever I'm going to do a graph. So let's see, if I put in x is 5, that's going to give me 5 minus 5, therefore 0. If I put in, let's see, negative 1, negative 1 minus 5 is negative 6. Negative 6 over negative 1 plus 3, which is 2. Negative 6 over 2 would be negative 3. If I put in negative 2, negative 2 minus 5, that's negative 7. Negative 2 plus 3 is 1, so that's going to be negative 7. If I put in 10, 10 minus 5 is 5. 10 plus 3 is 13, so this one's going to give me 5 over 13. What about some more negative numbers? If I put in negative 4, so negative 4 minus 5 is negative 9. Negative 9 over negative 4 plus 3, which is negative 1. Negative 9 over negative 1 is 9. I put in a minus 5. Minus 5 minus 5 is minus 10. Minus 5 plus 3 is minus 2. Minus 10, let's see. Minus 10 over minus 2 is 5. If I put in a negative 7, I'm going to 7 minus 5 is 2. 7 plus 3 is 10. Let's see if I had that right. 7 minus 5. No, negative 7, sorry. Negative 7 minus 5 is negative 12. Negative 7 plus 3 is negative 4. Negative 12 over negative 3 is 4. And then negative 11. Negative 11 minus 5, negative 16. Negative 11 plus 3, negative 8. So that gives me a 2. And you might say, well, why did you pick those numbers? And really, I'm just trying to go with ones that, unlike the 10 here, didn't give me fractions. All right, so I have a vertical asymptote at x equals negative 3. So that's going to be right here. So I know my graph can't cross there. And I'm going to have a horizontal one at y equals 1. So it's going to go right there. And then let's go ahead and start putting our points in. 5 was 0. So that's right there. Negative 1, negative 3. Negative 1, negative 3 would be here. Negative 2, negative 7. Negative 2, negative 7 is there. Negative 4. Let's see. Negative 4 was 9, so that's up here. Negative 5 was 5. Negative 7 was 4. Negative 11 is 2. And 10 was 5/13. So that's not quite half, so it's in this range there. So basically, one of the curves is going to go. There we go. Now we can see them all. One of the curves is going to go like this, and they get closer and closer to those asymptotes. And the other one is going to do a similar thing on this side. And it's going to go here, like that. And you can see with them both having x as their greatest term, well, it's not exactly the same. It's very similar to our first reciprocal function graph. Let's look like this. It is flipped from that a little bit because both of these had, because we had the x's and then x over x. So here's one, and then there is the other. All right. So here we have highest x squared for our terms. So again, we're going to take the denominator, set it to 0. This will factor into x and x, give me x squared. The inner is negative 5x. The outer is positive 2x. Negative 5 plus 2 gives me my negative 3. Negative 5 times 2 gives me my negative 10. So this will give me vertical asymptotes at x equals 5 and x equals negative 2. So now we're going to take the function, and we're going to divide everybody by x squared because that's the biggest power, and they are the same in the numerator and denominator. So I'm going to get 4x squared over x squared plus 4x over x squared minus 24 over x squared. So all the terms in the numerator divided by x squared. Denominator x squared divided by x squared. And then minus 3x divided by x squared. And then minus 10 divided by x squared. Now, as x goes to infinity, all the terms that do not have the same x squared on top and bottom, because those will cancel, they're going to become insignificant. They're going to go towards 0. So all that's going to leave me with is f of x is basically going to go towards 4. This x squared over x squared will be 1. And x squared over x squared will be 1. So it's going to go towards 4 over 1. So that gives me y equals 4 as the horizontal asymptote. And then finally, if I want to find the y-intercept, so f of 0, 0, zeros, I'm left with basically negative 24 over negative 10, which is basically negative 2.4. We'll just go ahead and leave it as a decimal, and that's the y-intercept. All right, so we have two vertical asymptotes, one at 5. So let's go ahead and put that one in first. One at negative 2. And then we've also got a horizontal one at 4. So these are the lines my graph won't cross at certain portions. And you'll see how this works in just a moment. So let's go ahead and do some points. Okay, we're going to do x and y. Make a little t-chart. So plug in negative 1. So that's going to give me 1 squared. Negative 1 squared is 1. So 4 minus 4, that's gone. So that's negative 24. In the denominator, that's 1. Plus 3 minus 10, that's 6. So we're going to get a 4 here. If I put in a positive 1, I actually end up with 4/3. If I put in 2, let's see, so that's 4 times 4 plus, that's 16 plus 8 minus 24, the numerator is 0, so that one's 0. Continuing on. Let's do 3. 3 ends up being negative 2.4. I'm not going to go through all of the calculations. You can repeat those if you want. Let's see. Negative 1.5 is 6.5. Let's see. Negative 3 is 0. Negative 2.5 is negative 2.4. 5 is 1.9. Obviously, I'm doing a little bit of rounding here. Negative 10 is 2.8. And just a couple more. Not every graph you do will have this many parts. Let's see. Negative 15 is 3.1. 6 gives me 18. 10 gives me 29. 7 gives me 11. Boy, that sure shifted, huh? Some more. 15 gave me 5.5. And 20 gave me 5. So, did quite a few there, but let's see where things are now. So here's 0, 0. So negative 1 was 4. So negative 1 is 4. So that's right there. And 1 was 4/3. So 4/3 is just about there. And 2 is 0. So that's there. 3 was negative 2.4, so it's about there. 4 was negative 9.3, so not quite 10. There. Let's see. We'll do 5. We'll do 5. Okay, let's see. What else do we got? We got negative 1.5 is 6.5. So 1.5, 6.5 would be 6. That's about right there. Negative 3 is 0. 1, 2, 3. That's there. Negative 2.5 is negative 2.4. So 1, 2.5, 2.4. Let's see. Oh, down here. So 2.5, 2. It's about there. Negative 5 is 1.9. Positive 1.9 is almost 2. Negative 10 is 2.8. So it's almost up to 3. Negative 15 is 3.1, so just barely above 3. 6 was 18. So 6, 18, that's way up there. 10 was, oh, sorry, 10 is 7.9, not 29, 7.9. So 10, here's 10, 7.9, so almost 8. 1, 2, 3, so it's about in there. 15 was 5.5. It'll be about there. 20 was 5, so that would be right there. So basically, what we're seeing, let me shift this around so it's easier, is basically I'm going like this. And then this middle one is going to go up like that. And then this bottom one is going to go like this. And so it actually got broken into 3 different sections, of which, the vertical asymptotes bounded these 2, and the horizontal one bounded them as well, but it did not bound Interestingly, the middle piece that went through the middle there, it did not bound that one. But now, that did take a lot of points to get a real good feel of what it looks like. But you can imagine if you were trying to do this graph without being aware of where the graph can't cross, how easy it would be to get very confused about, how am I supposed to take these points and these points and these points? I would have some kind of really strange graph when it turns out that what's really going on is it's been broken into 3 different parts where those red lines, if you will, can't cross. And so that is our final section.